Okay, here we are going to complete the notes for Chapter 3, Part 2. This is going to cover empirical and molecular formulas. So, molecular formulas, a molecular formula is the actual formula of a molecule. A molecule, and this is something that we'll cover in greater detail later when we talk more about the difference of different compounds. But a molecule is a non-ionic compound, and so it's a covalent compound made up of a nonmetal plus a nonmetal. So this is something that we would have used named using prefixes. These are not ionic compounds. Molecular formulas only deal with molecules. Empirical formulas can include ionic compounds. Ionic compounds always only have empirical formulas. So an empirical formula is a chemical formula with subscripts showing the smallest whole number mole ratio. So BH3 is the empirical formula of B2H6, B3H9, B4H12. CH2 is the empirical formula of C2H4, C3H6, C4H8, and so on. And so these are all nonmetal and nonmetal covalent compounds. If you remember from ionic compounds, we always had to have the simplest form. And so, for example, when you would put together barium, I'm going to need a new one, barium and oxygen, it's a +2 and a -2 charge. Ba2O2 was not acceptable. We had to simplify that to get BaO. That's its empirical formula. So ionic compounds, the way they exist, exist in discrete units, and so we need the empirical formula. Whereas covalent compounds here with nonmetals exist in these molecules, and so we can have different molecular formulas with one empirical formula. BH3 is very different than any of these. CH2 is very different than any of these. That's not the case for the ionic compounds. The relationship between empirical and molecular formulas is this, where you have a whole number multiplied by the empirical formula to get the molecular formula. So the empirical is just the simplest form of that molecular formula. So, for example, the reason why this is important is for these problems here. So this problem says quantitative analysis shows that a compound contains 32.38% of sodium, 22.68% of sulfur, and 44.99% of oxygen. Find the empirical formula of this compound. So we're going to start with follow these steps. The first thing we're going to do is convert percentage to mass, and the reason we're going to do that is we're going to assume we have a 100-gram sample. And so since they're giving us a percentage, the easiest thing for us is going to be to assume we have a 100-gram sample, and that makes all of those grams. And so we've got 32.38 grams of sodium. If we had a 100-gram sample, it doesn't matter what sample we use because we're trying to figure out the formula where you're not trying to actually figure out something based on this substance. Okay. So once I do that, I want to convert grams to moles. So we've done this step. Now we want to convert grams to moles. So I'm going to do that by putting grams on the bottom, moles on top. I want to cancel out grams and end up with moles. And so I'm going to do the same thing down here. Grams of sulfur to moles of sulfur. Grams of oxygen to moles of oxygen. 1 mole of sodium, 22.99 grams of sodium. Just get that from the periodic table. 1 mole of sulfur is 32.07 grams of sulfur. 1 mole of oxygen, 16.00 grams of oxygen. Put that in our calculators. So I get 1.408 moles of sodium. Here 0.7063 moles of sulfur. And 2.812 moles of oxygen. So I've converted to moles. Now I want to divide by the smallest because I'm trying to find out the relationship of these to each other. And so I'm going to figure out the smallest, that's sulfur. 0.7063 moles of sulfur, and so that's 1. So we have 1 mole of sulfur here. Here, divide by 0.7063 moles of sulfur. Here, I'm trying to get a whole number, and so I'm going to approximate. We're not worried about significant figures here because we're trying to find a formula and their relationship to each other, and so this is about equal to 2. It's 1.999 something. So this is 1 mole of sulfur, 1 mole of sodium, and here if I divide by 0.7063 mole of sulfur, so this is all in relationship to sulfur, then I get about 4 moles of oxygen per 1 mole of sulfur. And so what this is telling me here is that for every 2 moles of sodium, I have 1 mole of sulfur and 4 moles of oxygen. That's their ratio to each other. So the whole point of this is trying to find their ratio to each other, which is essentially the empirical formula. And so that means that the empirical formula would be Na2S1O4. And so what we have here is sodium sulfate. That is the empirical formula of this substance. There wouldn't be a molecular formula for this substance because this is an ionic compound. Ionic compounds exist as large quantities of cations and anions. So if you think of a salt crystal, all ionic compounds are these large crystals, and so they're not in the units that molecules are in, and so therefore we always write their formula in terms of the simplest form. And so the empirical formula for this compound is Na2SO4. Here we have, it says, analysis of a 10.150 gram sample of a compound known to contain only phosphorus and oxygen indicates a phosphorus content of 4.433 grams. What is the empirical formula of this compound? So here, since we're given a sample, mass of the sample, not percentage, here we can immediately start with converting grams to moles. We have, indicates phosphorus content of 4.433 grams. So we know we have 4.433 grams of phosphorus. And we have, whatever's left over is our oxygen. And so it's 10.150 grams minus 4.433 grams. Should get 5.717 grams of oxygen. So 5.717 grams of oxygen. Grams of phosphorus, moles of phosphorus. For every 1 mole, we've got 30.97 grams. Grams of oxygen, moles of oxygen. For every 1 mole, we've got 16.00 grams. Put that in my calculator, 0.1431 moles of phosphorus, 0.3573 moles of oxygen. This is their relationship to each other. So I'm going to go ahead and divide by the smallest number because I want the ratio of them to each other. So this is 1. Here, if I put this in my calculator, I get something that I can't round up to 3 because it's about, let's see what I actually get. If I put in 0.3573 divide by 0.1431, I get 2.4968. So if I'm going to round that up, it's going to be closest to 2.5. And so what that means is that I don't have whole numbers here, but I can get there pretty easily if I just multiply each of these by 2. And that's okay because I'm multiplying both of them by this. Think of it as a fraction. If you multiply the numerator and denominator by the same thing, then it's effectively the same. So the same thing here, we're looking at the ratio to each other. And so as long as we multiply both by 2, it'll still hold true. And so here then it would be a 2 and a 5. And so therefore the simplest whole numbers of this is P2O5. So we could have written that it was P1O2.5, but we don't write formulas that way. We had to multiply that by 2 in order to get this simplest whole numbers. That is the empirical formula of this compound. We don't know if it's a molecular formula because we're not given the molar mass of this substance, but it could have a larger or different molecular formula based on the molar mass. So, and in the next one, it tells us that in that sample problem, the empirical formula was P2O5. Experimentation shows that the molar mass of the compound is actually 283.89 grams per mole. What is the compound's molecular formula? And so here what I want to do, so here's the molar mass of the molecular formula. Now I want to find the molar mass of the empirical formula. Empirical. And so the empirical formula is P2O5. So we've got 2 phosphoruses at 30.97, 5 oxygens at 16.00, and so I should get 141.94 grams per mole. So then all I have to do is figure out how many times that goes into that number. And so I'm going to take 283.89, divide by 141.94, and I get something pretty close to 2. And so what that tells me is that it's twice as heavy as its empirical formula. So we just take 2 times P2O5, and we end up with P4O10. That is our molecular formula. So that's what the compound actually exists as. Here is its simplest form. But it exists with 4 phosphoruses and 10 oxygens as one unit. And so that gives us more detail about what compound we actually have. Okay, I am going to let you guys work on this next one on your own, but I'm going to give you the answers so that you can do that. And so for number 1, what you should end up with is C6H6. And for number 2, you should get H2O2, which is hydrogen peroxide. So if you have trouble with that, then let me know. And this is some practice for you to do, but then there's also practice problems in the practice module in this session. So please let me know if you have any questions. If you are confused with anything, I would be happy to make any more videos that you would need to explain this to you. Okay, that's it for today.